So we are looking at zeros of polynomials. So this is a part in college algebra of things that you probably haven't seen before. And so in your mathematical careers, you've only probably been able to solve for zeros of linear functions and quadratic, and then some that we can manipulate to look like quadratic functions. So now we're going to look at degrees that are higher than degree 2 or degree 1. And we're going to be given all these different rules and tools to be able to find zeros of a polynomial, if they exist and what they are. So there's going to be a lot of different theorems today and a lot of things kind of tying together. And we'll start with that. So I'm going to mute everybody, but you can come back in, and if you have a question, let me know, or any problems with the sound, let me know. Okay, so first of all, division. Division can help us break down a polynomial that is a higher degree into multiple factors. And we talked about earlier in the semester that we could take a polynomial and we can actually break it down in terms of factors of linear and or quadratic, depending if that quadratic was not reducible over the real numbers. And so if you we're looking at something, let's say P of X all over, I don't know, D of X. If you divide it, then you get something, some quotient, Q of X, plus your remainder. If that remainder is 0, then we know that that polynomial goes in there evenly. And this is all over, if it's written in this way, D of X. Okay, so just terminology, we call Q of X, is the quotient. P of X, that's what we're dividing into, is called the dividend. D of X is called our divisor. Q of X is our quotient. And R of X is equal to our remainder. So I can take this right here, and if I cleared my fraction, if I multiplied both sides of my equation by D of X, well, my left-hand side of the equation, D of X would cancel, and I would just get my P of X, what I was dividing into, is equal to my quotient times my divisor, D of X, plus, well, if I multiply this both sides by D of X, when I multiply this R of X over D of X by D of X, the denominator cancels with that and just leaves me with the remainder R of X. If R of X is equal to 0, that's what we're looking for a lot today. We're trying to break these down as factors. So we're trying to find when our remainder is 0. So this is the same thing as saying when the remainder equals 0. Then the quotient, then Q of X and D of X are factors of our polynomial P of X. So any factors of our quotient will also be factors of our original polynomial. So we're going to try to be breaking this down into smaller and smaller pieces. So if I'm looking at P of X and I'm trying to break this down into linear factors, I'm going to find some quotient here and a divisor. Those are going to be factors if my remainder is 0, but I'll be able to take this quotient if it's not of degree 2 or smaller and be able to break it down. I guess if it's degree 2 or smaller, I'll be able to do that too. Maybe, possibly. but I'll tell you more about that in a minute. Okay, so we have a theorem. And so today we're going to be dividing a lot of these polynomials by factors in the form of x minus c. So suppose, and this is called the remainder theorem. And it says, suppose that f is some polynomial function, and if f of x is divided by something in the form of x minus c, then x minus c, we'll get to that in a second, then the remainder is f of c. Okay, so this is kind of a cool theorem. So if we're dividing by something in the form of x minus c, if we look, what we're trying to find are when our remainder is 0. So if we wanted to find out if x minus c is a factor, we could just plug it in opposite sign c, and wherever we see an x in our function f of x, and if we get back 0, then we know it's a factor. If we don't get back 0, that number we get back would have been the remainder we would have gotten if we had done long division or synthetic division, which we'll talk about in a minute. So this remainder theorem comes to an important theorem called the factor theorem, which I was just mentioning. So what this factor theorem says is, again, we need to suppose that our function f is a polynomial. So suppose f is a polynomial. Then x minus c is a factor of f of x if and only if f of c equals 0. Okay, so if and only if means it goes back and forth. So if I had found that f of c equals 0, then I would know a factor of my polynomial. I would know it'd have to be x minus whatever this number was. Or if I divided x minus c into my polynomial f of x, then my remainder would be back 0. Would be 0 if this was a factor. So I'm not going to prove that to you. But let's look at an example real quick. Okay, so use the remainder theorem to find the remainder when f of x is divided by x minus c. Then use the factor theorem to determine whether x minus c is a factor of f of x. Okay, so for instance, if we're given that f of x is equal to the polynomial of negative 4x cubed plus 5x squared plus 8. And we want to know, is x plus 3 a factor? So first it says use the remainder theorem. To find the remainder when f of x is divided. is divided by x minus c. Okay, so we want to look at f of c here, and so we have to figure out what c is. And so our c value here, well, if I put it in the form of x minus c with a minus in here, this is x minus a negative 3. So my c value in this case is negative 3. That's where I was just saying it's just the opposite sign of what is in here. So this theorem says, well, if we can find the remainder, if we'd done long division of x plus 3 into this polynomial of f of x, if we find f of negative 3, so we need to go back into our equation f of x, and we're plugging in negative 3 wherever we see an x. So let's just go in there, put a parentheses wherever we see an x, and we'll replace it with negative 3. So we have negative 4 parentheses, and then cubed, plus 5 parentheses, then squared, plus 8. Plugging in negative 3 wherever we saw an x, which is where we just had the blank parentheses. Okay, so this is equal to, well, negative 3 cubed is negative 27 times this negative 4 out front. So negative 4 times negative 27 plus 5, and then squaring negative 3, that gives me 9 plus 8. So order of operations, you first do exponents before multiplication. So 4 times 27, or negative 4 times negative 27 is 108. Plus 5 times 9, which is 45, plus 8. So right now I can see that this is not equal to 0, but it wants the remainder. So 108 plus 45 plus 8 gives us 161. So we have our remainder. Which we called r of x, equals 161. So I want to go through and do long division, and then I want to show you synthetic division. So this section assumes that you know synthetic division, so I just want to go through it really quick. But x plus 3, if we've done long division, because this is basically, we're dividing this into f of x, and then we are going to do it with synthetic. We can only use synthetic when we're dividing in the form of x minus c, which we're using in both of these theorems. And so remember when we were writing our polynomial, our dividend underneath the division symbol, we had to put a placeholder for any terms that were missing power. So I have a negative 4x cubed here. I have a plus 5x squared, but I'm missing x term, so I'm going to put plus 0x plus 8. So long division, we only looked at the first term when we're doing long division of polynomials of our divisor and the first term of our dividend. And we think to ourselves, what can we multiply x by to get back negative 4x cubed? And that's negative 4x squared. We took that number and we distributed it. And so this is negative 4x cubed. This would be negative 12x squared. And then we subtracted this off. Or same thing as adding the opposite sign. So this is a negative 4x cubed, really plus a 4x cubed cancels, which was the whole point of choosing what we did. This is a 5x squared, but this is minus and negative, so plus 12x squared, 5 plus 12, so this is a 17x squared. Bring down our next term. I guess we could bring them all down if we wanted to, plus 0x. So continue that. So you're looking at 17x, and you're looking at what can we multiply x by to get back, I'm sorry, 17x squared. What can we multiply x by to get back 17x squared? Well, that's a positive 17x. Distribute it. 17x times x is 17x squared. 17x times 3, that's big, 51x. Subtract that off. Add the opposite. 17x squared minus 17x squared cancels. And this is 0x minus 51x is negative 51x. Bring down the plus 8. Okay, so what are we multiplying x by to get back this first term down here, which is negative 51x? That would be minus 51. Distribute it. Negative 51x. 3 times negative 51. That's 153, and that would be a minus. Subtract this off. So this is positive 51x minus 51x cancels. This is really 81 minus 153, minus a negative 153. So 8 plus 153, which is 161. So notice our remainder is equal to what we got when we looked at f of negative 3, which by the remainder theorem said that's what would happen. So I wanted to show that that does happen, but I also wanted to show the long division and then show you the synthetic division. So with synthetic division, if you divide in the form of x minus c, we can use synthetic division only if it's in that form. And so notice in that form, that coefficient in front of x is positive 1. Okay, so we can use synthetic division when our divisor is in the form x minus c. So I just want to walk you through the process. And so you're going to take your value c. So I've learned it differently. Your book kind of does it a little differently. They kind of keep this division symbol here. I've learned it where I put my c value up here in the corner and kind of half of a box. And then the first row, they call these rows. These are the coefficients of what you're dividing into, so the dividend. Put 0 as a placeholder. For missing terms. And then this also has to be in descending order of powers. So list the coefficients of those terms in descending order of powers. Okay, so let's just do that with what we have so far. We were dividing by x plus 3. And so our c value we saw was negative 3. And so we're going to put negative 3 up here in our corner. And then we want to list the coefficients in descending order of powers. So if we look back here, our coefficient of our first term was -4. So we have -4. Just do this. So we have -4. Then we have a 5. Then we have a 0. And then we have an 8. So -4. Then we have a 5, 0, and 8. So once you have that listed, descending order of powers, just the numbers in front, you're going to bring your first number down and multiply it by C. Once you multiply it by C, you're going to put it underneath the next number in the first row. So this is going to be -3 times -4 here. So that's +12. We sum them. So 5 plus 12 is 17. Normally I don't put that right there. 17. And so we have to do the same process as before. We have to multiply that number down there that we just brought down, summing it, and multiply it by -3. So this is -3 times 17. So that would give us 51. And then sum it and bring it down. So 0 plus 51 is 51. Multiply that bottom row by your C value, so -3 times 51.
Would 51 be negative?
Yes. And so this would be negative. So this would give us -103. No, 153. That would be positive because 2 negatives now is positive. We sum this up. This gives us 160. Wait. Yeah. Is that what we got? Yeah. Okay. So notice this last number is the remainder. Let's also go look at what we got for our quotient up here when we actually did the long division. So notice our quotient up here, this -4x squared plus 17x minus 51. This is the exact same numbers, -14, 17, -51, as our coefficients in front of these terms. So that's always going to be the case. And so this is always going to be your quotient. Last number is the remainder. All the other numbers before the last number are going to be the coefficients of your quotient. You always start 1 degree less than what our original polynomial is. So this is our quotient. Or maybe coefficients. And the quotient. The quotient is 1 degree less than what you're dividing into, so the dividend. So here we had what, a degree 3 polynomial that we were dividing into. So that tells me that that first coefficient is of the x squared term, 1 degree less. And so this here I could write as my quotient, q of x, is equal to negative 4x squared. It's positive, so plus 17x minus 51. So the other question, and I went through this more in detail than what the question the book was asking to explain stuff, but it was also asking, is that quotient a factor of our dividend? Well, we didn't get a remainder of 0, so it doesn't go in evenly, and so no. So by the factor theorem, it's not, because the remainder is not 0. So let's look at one more with using this theorem. Same question, but we have f of x is equal to 2x to the 6 minus 18x to the 4th plus x squared minus 9. And we're trying to see about x plus 3. Let me just make sure I wrote that down right. So f of x is 2x to the 6 minus 18x to the 4th plus x squared minus 9. Okay, so it asked us to use the remainder theorem. So technically I can use the remainder theorem, or I can use synthetic division and see if my remainder is 0. It actually is sometimes faster to use synthetic division than it is to take a -3 and go in and plug it in wherever you see an x in this. And so let's just do it then. So I want to just get practice of synthetic division, because I know that you guys hopefully know how to plug in f of -3. So let me just put -3 up here. And then we want to write the coefficients, just the coefficients in front of our polynomial of f of x. So, and I need to put 0 for any terms that are missing in this descending order of power. And so I have 2. I don't have an x to the 5th, so I'm going to put a 0. I don't, then I have -18. I don't have an x cubed. I'm going to put a 0. Then I have an x squared, which is 1. I don't have an x term, so I put 0. And then the -9. So bring down our first number, 2, multiply. -3 times 2 is -6. Sum. 0 plus -6 is -6. Multiply. -3 times -6 is positive 18. -18 plus 18 is 0. Multiply. -3 times 0 is 0. Put it below. 0 plus 0 is 0. -3 times 0 is 0. 1 plus 0 is 1. -3 times 1 is -3. Sum. 0 plus -3 is -3. -3 times -3 is 9. And I get 0. So that might have been a lot faster. We could have had a race of you going in and plugging in -3 wherever you saw an x, raising it to the power, multiplying it by the coefficient in front, and then summing the whole thing. But I think this a lot of times is much faster. So it's just a tool that will help us with division. And so notice our remainder is equal to 0. that tells me then x minus 3 is a factor of f of x. And so right now we can rewrite f of x as x minus, oh no, it was x plus 3. So I can rewrite f of x as x plus 3. And so we talked about this being the coefficients of our quotient, and it's 1 degree less than what we had started. So this is going to be 2x raised to the 5th power. So descending order of power. So this would be minus 6x to the 4th. I don't have a x cubed. I don't have an x squared. I have 1x, so plus x. My constant is minus 3. So hopefully by break time, you'll be able to go through and actually go down with the tools that I'm going to give you and be able to factor this down to linear and or quadratics. Okay, so there's lots of theorems in here. Theorem that says if you have a degree of your polynomial, there cannot be more zeros than our degree. I tend to do things a little different in order, so I'm going to give you the next theorem that I tend to talk about, which is called the rational zero theorem. Okay, so the following has to hold in order to use this theorem. So what this rational theorem says is let f be some polynomial. So it has to be a polynomial. Of degree 1 or higher. Of the form like we were writing them before. So f of x is equal to a sub n x raised to the nth power plus a sub n minus 1 x raised to the n minus 1 power, so descending order of powers, plus dot 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 plus a sub 1 x plus a sub 0. And our constants don't equal 0. Constant doesn't equal 0, and our leading coefficient doesn't equal 0. This is what I was looking for. So we have to say that these coefficients are integers. Coefficient is an integer. So if you have some polynomial like this, then if f of x has rational zeros, It has to be in the form, or it has to be a number in the form, I guess I'll say it that way, P divided by Q, where P is equal to all the factors of your constant which is a sub 0, and Q equals all the factors of your leading coefficient. Okay, so let me just kind of explain how huge this theorem really is. So basically, we can find any value which set our polynomial equal to 0. We know that the degree that there has to be at least that, or there is that number of zeros, and that includes multiplicity when we're counting multiplicity. Well, we didn't know how to factor things before if it wasn't quadratic, but now we can break this down and factor it. And so we can list or narrow down the infinite numbers out there. And this is telling me if there's some 0, so it has to be in rational form. So that's telling me integers can be written in rational form, because 2 could be written in the form of 2 over 1. If it does have a 0, then it has to be one of these. And so let's look at this. So basically, and I don't know if it goes any further, actually this is ugly. That would be telling me here, if I wanted to break this down, I would be looking at the factors of my constant 3, or negative 3, and I would look at the factors of my leading coefficient 2, and I would look at all the different values that could be of P over Q. And if it had a 0, it would be one or more of those. But if the 0, it would have to be one of those. Let me see. So I want to kind of start with not fractions in there. So let's look at another an example. So let's say you're given that f of x is equal to x cubed plus 8x squared plus 11x minus 20. So if we wanted to find the zeros of this polynomial, so the zeros are another way to say, if we're going to graph it, the places where this will cross the graph, cross or touch the x-axis. Let's list all the possible rational zeros. Of f of x. Okay, so P, that are all the numbers that divide evenly into our constant. So our constant, a sub 0, in this case, I never carry the sign because of the plus or minus here. So numbers that go evenly into 20, and I always go from smallest to highest. So 1 is a number, that always goes into another number. So 1, 2 goes in there evenly, 3 does not, 4 goes in there evenly, 5 goes in there evenly, 6 does not, 7, 8, 9, 10 goes in there evenly, and itself 20 goes in there evenly. So here are all the factors that would go evenly into our constant. So look at all the factors now that go evenly into your leading coefficient. So my leading coefficient here, so it's the number in front of it's the number for the leading term. So our a sub n on our case is 1. So there's only two numbers that go evenly into 1, positive and negative 1. So if I look at p divided by q, so we're going to take every number in p and divide it by every number in q. Well, we're lucky because there's only one right now. So plus or minus. So we have 1 divided by 1 is 1. 2 divided by 1 is 2. 4 divided by 1 is 4. 5 divided by 1 is 5, etc. 10 and 20. So in this case, it just happened to be plus or minus factors of our constant. So we'll list all the rational zeros. So if it has a rational zero, it would be one or more of these numbers, but it would not fall outside of this set. So 3 could not be one of the rational zeros because it's not in this set. So we've listed or limited down an infinite number to a finite number. And so now we can start checking. So let's use synthetic division to find which ones are actually zeros of this polynomial. Part B, let's just find the zeros of the polynomial. Okay, so I'm just going to start using synthetic division, and I'm going to test it and see, or you can plug that number in for x to see if you get back 0. I'm going to list my coefficients in descending order of powers. It looks like that I don't have any degree, a term with a degree missing. So my coefficients are 1, 8, 11, and negative 20. And I'm going to first test 1. So bring down our 1. 1 times 1 is 1. Bring it below, and then sum the next number. So 8 plus 1 is 9. 1 times 9 is 9. 11 plus 9 is 20. 1 times 20 is 20. And I get back 0. Yay. That normally doesn't happen at the first number I try. Works. So we have a remainder of 0, and that tells me that 1 is a 0, but it also tells me what a factor is. So x equals 1 is a 0 of f of x, and if I subtract 1 on both sides, x minus 1 is a factor of f of x. So far, we can rewrite our polynomial f of x as the factor x minus 1 all times our quotient. And we can determine what that quotient was by looking at the bottom row of our synthetic division. So our quotient, 1 degree less than what we started at. We started with a cubic, x cubed. And so this is now going to start at a square. So this is 1x squared, or just x squared, plus 9x plus 20. So I'm going to take this quadratic and we can break that down further to find the zeros. Well, a couple things. If it's quadratic, then you should be able to find the zeros of that. We can either factor it, or if it is not factorable, we would use the quadratic formula and see that it wasn't factorable. and now we got something other than a rational zero. This list does not give me any numbers or solutions or zeros that are not rational. I notice here that this actually factors further. I could use the synthetic division and keep testing numbers and see when I get back 0, or what multiplies to 20 and adds to 9. Well, that is 4 and 5 multiplied to 20, add to 9. So this would be x plus 4, x plus 5. And so from there, without going and testing using synthetic division, I can tell that what the remaining zeros of f of x are. So this is equal to 0 when x is negative 4. X plus 5 equals 0 when x is negative 5. And then we already saw x minus 1 was 0 when x was 1. Those are all rational numbers, and they were all in our list up here. So I would ask you probably on a test that, find the zeros of a polynomial, and I would ask you to rewrite your polynomial in terms of linear factors and or quadratic that aren't reducible. And so here is f of x rewritten as a product of linear factors. Okay, so this could actually get kind of tedious. What if, your constant had a huge, long list of factors? This one actually had quite a few. Or maybe we had our leading coefficient might have a lot of factors. And so there's other theorems that can help us actually limit down what numbers we need to test. And so let me just start with what is called the upper bound and lower bound theorem. So usually I'll use that rational zero theorem to find the possible rational zeros. And then while I'm testing these numbers in my synthetic division, there's certain things that are going to put up red flags that there's no other numbers to test because of, and I'm going to tell you right now. So this is called the upper bound and lower bound theorem. Want their terminology. I don't like that. Basically, we say C, or x equals C, is called an upper bound of the zero of a polynomial if you're looking at the bottom row of your synthetic division and it's all positive numbers. So x equals C is a upper bound of the zero polynomial f of x if the bottom row in the synthetic division are greater than or equal to 0. One other stipulation here, the number that we're testing, x equals c, this has to be positive. So c is greater than 0. So we can never use this theorem when we're testing a negative, or the upper bound piece, when we're testing a negative number. Only when the number we're testing is positive. So notice back here when we did that synthetic division, that bottom row was all positive numbers. So 1, 9, 20, those are all positive numbers and 0. So that would have flagged me right there. I wouldn't have to test any numbers that were bigger than 1. So that would have gotten rid of a huge, number of values that I would have to test. I know now that I would start testing negative numbers. So that's what the upper bound theorem says. The lower bound theorem says, well, our value that we're testing actually has to be a negative number. So if we're looking at maybe x equals b, where b is less than 0, we say b is a lower bound. Of the 0 of our polynomial. If the bottom row is alternating in signs. Zero can count as positive or negative. Okay, so if we looked at the bottom row and one's positive, then we got a negative coefficient, then we got a positive coefficient, then negative, and it keeps jumping back, then we know that that has to be a lower bound, and that there's no other number smaller than that that could be a 0. Okay, so let's keep that in mind, but let me just give you the other theorem that can also help us find those zeros or limit those number of zeros that we have to test. And that's called Descartes' rule of signs. Okay, so I just want to make sure I have all the qualifications for it. So suppose f is a polynomial function written in standard form. The number of positive real zeros of f either equals the number of variations in signs of a non-zero coefficient of f of x, or else equal to that number less than or even by an even integer. Okay, so basically what this says is if you're testing, let's so the number of positive possible positive real zeros is equal to the number of sign changes of, let's just call it f of x, or that number minus an even number. Okay, so Descartes' rule sign doesn't tell us what it is, what our zero is, but it tells us how many possible real zeros there are, positive real zeros in this case. So basically, let's go back to what we had before. F of x was equal to, what was it, x cubed plus 8x squared plus 11x minus 20. 8x cubed plus 8x squared plus 11x minus 20. So we want to count the number of sign changes between terms. And so if you look at the number of sign changes, so if I'm going from x cubed, 1x cubed to a positive 8x squared, this has no sign change. If I go from 8x squared to 11x, this has no sign change. But 11x to negative 20, this is a sign change. So if I count how many sign changes there are in my polynomial, so there's only one sign change. So this tells me, this theorem tells me that I have to have one positive real zero. So there's one sign change. So there is one positive real zero. Okay, so it said take that number and subtract it by an even number. But if I subtract that 1 by an even number, like 2, I get a negative number, and it doesn't make sense to have a negative number of zeros. So if you ever get down and you keep subtracting, that number of sign changes and you get to 0 or negative, you stop. So right here, if I had known this before, I knew this before, I would have known that I'd only have one positive real zero. And so when I had found that number 1 was a zero of my polynomial, again, that would tell me I wouldn't have to look any further. There's no other positive real zero that works. And so to figure out how many negative zeros there are, and this is just the possible number. So number of possible zeros of a polynomial p of x or f of x. What you're going to want to do is you want to look at plugging in the negative of that variable. So in this case, f of negative x. Count the number of sign changes of that. And this is going to equal the number of possible zeros or negative zeros. This is the number of possible negative zeros, or this number minus an even number. Okay, so if I go back up and I plugged in negative x wherever I saw an x in my original function, and I counted the number of sign changes. So if I go in, I have an x cubed, I have plus an 8. I'm going to put a parentheses wherever I see an x. X squared plus 11, I see an x minus 20. So go in there and plug in negative x wherever you see an x and count the number of sign changes once you kind of reduce this. So negative x cubed times negative x cubed times negative x cubed. So that could be rewritten as negative x, then quantity cubed. Negative x times negative x, that's positive x squared times 8. So this could be rewritten as plus 8x squared. 11 times negative x, pull the negative out front, so minus 11x minus 20. So now we're going to count the number of sign changes in between each term. And so I have a negative x cubed to a positive 8x cubed. So this is one sign change. I have a positive 8x squared to a negative 11x. So this is another sign change. And then negative 11x to negative 20 is not. So I have two sign changes. For f of negative x. So that tells me there is either 2 negative zeros, real zeros, or 2 minus an even number. So 2 minus 2 is 0. Or no negative zeros. Real zeros. Okay, so where this could be helpful is I know there's either 2 or 1. So if I find one real zero, then I know there has to be another one out there. If there is 0 negative real zeros, then I know if there's one positive one and there's no negative ones, those other two have to be imaginary or rational. Non-rational. Let me just make sure that that had to do with rational. I know, might not. The number of negative zeros. No, it holds stronger than that rational zero theorem. So this is all real zeros. So if I didn't find a real zero, then the other two would have to be complex, negative. And that's what the next section talks about, is finding, going and doing what we're doing right now, but taking it a step further and finding the complex zeros of our polynomial. I want to blow this up so my pen is bigger. So let's say we had following, and let's use some of these theorems to help us. So we have f of x is equal to 4x to the 4th plus 5x cubed plus 9x squared plus 10x plus 2. So let's find all the zeros of f of x. And rewrite f of x of a product of linear and or irreducible quadratic factors. Okay, so we're going to use some of these theorems to help us. And so let's first look at the rational zero theorem. So we're looking at P divided by Q. And so looking at P, so let's look at all the factors of our constant, which is 2. So all numbers that go evenly into 2 is just 1 and 2. And then Q are all factors that are divisible, or numbers that are divisible into our leading coefficient. So numbers that go into Q, well, numbers that go evenly into 4 are 1, 2, and 4. So if I look at P divided by Q, so this is equal to, well, 1 divided by 1 is 1. 1 divided by 2 is 1/2, and 1 divided by 4 is 1/4. Okay, so now take the next number, P, and divide it by Q. So 2 divided by 1, that's 2. 2 divided by 2 is 1. If the number is already in your list, don't rewrite it. So 2 divided by 2 is 1. We already have it, we don't need it. And 2 divided by 4, well, that reduces to 1/2. We already have it. Okay, so if it has any rational zeros, it would be one of these. And let's look at Descartes' rule of signs real quick. Descartes' rule of signs, notice f of x. If you look at the number of sign changes in f of x, how many do you have? So looking at the number of sign changes in f of x, well, 4x to the 4th to 5x cubed is none. 5x cubed to 9x squared is none. 9x squared to 10x is none. And 10x to 2 is none. Okay, well, that just limits or takes half of my list away that I have to try. No sign changes, so that means no positive real zeros. So let's look at real quick f of negative x. When we plug in the negative in for x, let's also reduce it while we're doing it. So I have 4 and then a negative x all raised to the 4th. That's going to make it positive. So this is just a 4x to the 4th. When I plug in negative x for the x cubed, that's going to make this a, well, negative x cubed is a negative with a positive 5 coefficient in front is minus, so minus 5x cubed. Plugging in negative x for the x squared, that's positive x squared, positive coefficient of 9 in front, so plus 9x squared. 10 times negative x, so minus 10x plus 2. So looking at the sign changes there, well, 4x to the 4th to negative 5x cubed, this is one sign change. Negative 5x cubed to a negative or positive 9x squared is one sign change. Positive 9x squared to negative 10x is one sign change, and negative 10x to 2 is a sign change. So we have 4 sign changes. So this tells me there's either 4, subtract that by an even number, 4 minus 2, which is 2. I just keep subtracting by 2 until I get down to 1 or 0. So 4 minus 2 is 2, 2 minus 2 is 0. I don't have to have negative numbers. Or 4 minus 2 is 2, 4 minus 4 is 0, stop. So there's either 4, 2, or 0, negative real zeros. Okay, so we got our possible list. We actually now know that they have to be negative. And we can start testing, use our synthetic division, and if we show that our remainder is 0, we know we have a 0, and then we could figure out what the factor is. So I tend not to like to do fractions at first, so I would start with my -1 instead of -1/2. So let's put our C value that we're using, so -1, and then our coefficients. So our coefficients of f of x, that was +4, that was +5, that was +9, that was +10. They were all positives, weren't they? And 2. Other thing I'm looking at now when I'm doing my synthetic division is for my lower bound theorem. So are my last row, is that alternating in signs? If so, this would have to be the smallest number that was a 0 for negative. So bring down our 4, multiply it by c. So -1 times 4 is -4. Sum, 5 minus 4 is 1. 1 times -1 is -1. Sum with 9. 9 minus 1 is 8. -1 times 8 is -8. So nice. 10 minus 8 is 2. -1 times 2 is -2, and this gives me 0. So I get a 0 back as the last number. That's my remainder. So x minus 1 is a factor. X plus 1 is a factor. X equals -1 is a 0. If I add 1 to both sides, x plus 1 equals 0. I can look at my bottom row, and my bottom row starts 1 less than what I was dividing into. And so this is going to be an x cubed. So let's just write this out here. So this is 4x cubed plus 4x cubed plus 1x squared, or x squared, plus 8x plus 2. Okay, so I don't want to go back to my original f of x and find the rest of the zeros with that. I've already reduced this, so if I have my remaining zeros of f of x also have to be factors or zeros of this quotient. And so it's easier if we just keep on making it smaller degrees. And so let's, instead of using our original f of x, let's use this quotient to find the rest of the zeros, excuse me. I could apply that p over q thing again. It didn't change anything. It just happens that I have the same constant and the same leading coefficient, which is not always the case. So 4, I'm gonna write this 4, 1, 8, and 2 are my numbers of my coefficients. I can either test -1 again, Or I can test another number that is possible, which is -2, -1/2, or -1/4. So it is possible, because of multiplicity, that our 0 could occur more than once. Maybe let's try -1 again. So let's bring down our 4. -1 times 4 is -4. Sum this. 1 minus 4 is -3. -1 times -3 is 3. 8 plus 3 is 11. -1 times 11 is -11. 2 minus 11 is -9. So our last number is not 0. So x equals -1 is not another 0. Still 0 up here, though. I also see my lower bound theorem happening. I'm alternating signs, +4, -3, +11, -9. So lower bound theorem says there cannot be a number smaller than -1 that is a 0. And so -2 is now no longer in my list that can work. Okay, so x equals there's no number smaller than -1 that works. By the lower bound theorem. Okay, so I want to go back and I want to try again. I've been lucky before. So we either want to try 1/4 or 1/2. Might as well try 1/2. And if that was, or -1/2. And if that is a lower bound, we'll find out real quick because we'll also alternate in signs. And so I have 4. I'm going to leave room because I need to deal with fractions maybe. 1, 8, and 2. Let's bring down our first number, 4. 4 times -1/2 is -2. 1 minus 2, that is -1. -1/2 times a -1 is 1/2. So get a common denominator. So this is 16/2 plus 1/2 is 17/2. -1/2 times 17/2 is -17/4. Common denominator. So this is an 8/4 minus a 17/4 is a -9/4. Okay. Again, this is alternating signs, so it is a lower bound, so -1/4 could work. So just rewrite the numbers above, 4, 1, 8, and 2. Bring down our first number, 4. -1/4 times 4, that's -1. -1 plus 1 is 0. -1/4 times 0 is 0. 8 plus 0 is 8. -1/4 times 8 is -2, 0. So x equals -1/4 is a 0. Let's rewrite f of x, knowing that if x minus 1/4 is a 0, usually we won't see it as x plus 1/4. I mean, we could write it like that, and I probably wouldn't mark you wrong, but we can make it so that there's no fractions. Let's multiply both sides by 4. 4 times x equals -1. Let's add 1 to both sides. So 4x plus 1 equals 0. So 4x plus 1, this is a factor. Of f of x. Okay, we also know that our quotient is the factor of f of x because our remainder was 0. And our quotient, we were starting before, this was an x cubed function. And so 1 degree less, or x cubed, is squared. So this would be a 4x squared plus 0x, I don't have to write that, plus 8. Okay, so far, we have f of x. One factor was x plus 1 when we found that -1 was a 0. One factor is 4x plus 1. We saw that when -1/4 was a 0. And we have our quotient here of 4x squared plus 8. Once I get this down to a quadratic, I'm not going to use synthetic division again. I think that's kind of silly. We can use our rules of finding the zeros by solving when it's 4x squared plus 8 equals 0. So I can use my quadratic formula. I notice I can use my square root theorem. So if I subtract 8 on both sides, divide by 4, so I have 4x squared equals -8. Divide by 4, I get x squared equals -2. I notice this is going to be a complex number, taking the square root of a negative number. So x is equal to plus or minus the square root of -2. So x is equal to plus or minus I root 2. So not reducible over the real numbers. And so notice that we found 2 zeros that were negative, the -1/4 and the -1. And Descartes' rule of signs said that would either be, 4, 2, or 0. And we found 2 of them. The other 2 of the zeros were complex. So we saw it was -1, -1/4. And we just saw plus or minus I root 2. If you count, there's 4 zeros, -1, -1/4, positive I root 2, and negative I root 2. Our degree of our polynomial is degree 4. So that is not a coincidence. That's also an important theorem. I'll give you one more theorem. And you'll be using this in Calculus 1, Intermediate Value Theorem. So basically, let's say, let A be less than B. If f of x is a polynomial, so let f of x be a polynomial. And if f of A and f of B are opposite signs, then there must be a zero. Between x equals A and x equals B. Which makes sense if you're thinking about some graph and you have some value x equals A, some value x equals B. One of them is positive, one of them is negative. It doesn't matter which one is which. And you have a polynomial. Polynomial graphs are always continuous. There's no jump in here. And so if I connect these 2 points somehow, it has to at least cross once. It could cross more than once, but it has to at least cross once. And so you can approximate that by making that interval shrink down further and further. Or you could make it so that you have your value of A, you know, it's positive or negative, and then start choosing values. And so they say, okay, sometimes they say like split it up into 10 intervals and then start checking it. But you could just add whatever that interval is to A and check that. If one is positive, one is negative, you know it's in between there. If not, you would move on. And you would see when that happens. Let me just do one of those. Each equation has a solution R in an interval indicated. Use the method, so this method, to approximate the solution correct to 2 decimal places. So I don't want to do it. Well, let's just do it. So let's say we have x to the 4th. This is where I don't mind you guys using Desmo, so I'm not going to have one where you would have to if it's going to go out so far. So we have x to the 4th plus 8x cubed minus x squared plus 2 is equal to 0. And they're telling us that there's some 0 that's falling between -1 and 0. Okay, so let's define f of x to be this polynomial, x to the 4th plus 8x cubed minus x squared plus 2. And let's evaluate f of -1. So we can do this by synthetic, or we can just plug it in. And we plug in -1. -1's not too bad though. -1 to the 4th power is 1. -1 cubed is -1 times this 8 in front, so that's -8. -1 squared is 1 with a negative in front, so -1 plus 2. So f of -1, this is equal to 1 minus 8 is -7. -7 minus 1 is -8. -8 plus 2 is -6. I just want to show that f of 0 should be a positive number. If you plug in 0 for f of x here, we get back our constant, which is 2. So this theorem, intermediate value theorem, says there has to be a number between -1 and 0, which we are given that this works. So you want to, let's make, like, split this up. So we have -1 here. So maybe let's try, I don't know, -0.9, we could, -0.8, -0.7. Oh wait, 0. So this again is where using the calculator could be really helpful with the Desmos, so we could already define what it is. I need to pull up my... So let me pull that up real quick. Maybe not. Okay, maybe maybe this will be a good place to take a break, and then I can get that typed in, and we can come back and I can show you and we can look at it during break. So let me pause this. So we just plugged this into Desmos, this function, and we're gonna plug in values that are between -1 and 0. We're trying to find values that it's changing sign. And once where we see that it's changing sign in between one of these intervals that we're looking at, then we can shrink the interval even closer. And so I went in and I plugged in the function. I looked at f of -1 and f of 0. And f of -1 was -6, which we had found before, and f of 0 was 2. So those are opposite signs, and so we know that there has to be a 0 in between these two. And so let's just shrink it down. And so maybe let's go halfway. So maybe f of -0.5. So notice here, when I do this, this is positive. And so this is positive 0.8125. And so I know then my 0 has to be between -1 and -0.5. And so let's shrink that interval even further. So maybe f of -0.3. So f of -0.3 is also positive at 1.75. And so -0.3, oh, actually, I'm sorry, I should have gone the other way. I should have gone between -0.5, and so this should have happened. I should have gone between -0.5 and 1. And so how about -0.8? So -0.8 is negative, and -0.5 is positive. And so we want to choose a number between -0.6 and -0.8. So what about -0.6? Okay, so -0.6, this is positive. -0.8 is negative. So we know that it's between -0.6 and -0.8. So how about -0.7? Oops. -0.7 is negative. -0.6 is positive. So it has to fall in between both of these. And so it has to fall in both of these. How about -0.65? Okay, so oops. negative 0.65, that's also negative. So we know that it's between this f of negative 0.6 and this f of negative 0.65. So let's do half of that. So what about 6.7, negative 0.67? Wait a minute. Yeah. So this is negative. What was I looking between? That wouldn't work. It was between negative 0.6 and negative 0.65. So it's the opposite direction. Sorry, the negative is throwing me off a little bit. So negative 6.3, negative 0.63. So this is also negative. So it's between negative 0.6 and negative 0.63. 2, 6, 1. And so we know it's between negative 0.6 and negative 0.61. And they gave us that it's negative 6.0. Why are they doing that? So negative 6.0 is where they're putting it. My guess is because rounding wise, it wouldn't round this up. Oops. So let's just look at that 0.9. So 0.9 is negative, 0.8 is negative, 0.6 is negative, 0.5 is negative. So 0.4, this is positive, and a positive. And so my guess is they did it so that it rounded it. Okay, so basically that intermediate value theorem, we can shrink intervals. If we have a polynomial, we plug in a value, one is negative, one is positive, it doesn't matter which side. Then there has to be a point where it's crossing the x-axis there, and that would be a solution to the equation, or zero of the polynomial. And so you can shrink down that interval until you see, very closely where that x-intercept would occur. So let's take what we've been doing with these polynomials and finding the zeros of a polynomial and put it all kind of together. So let's graph a polynomial. Take this out. Okay, so looking at the following, let's say that you want to graph f of x is equal to x to the fourth minus x cubed minus 6x squared plus 4x plus 8. So let's kind of put all of our pieces together. So let's first look at what's going to happen to the end behaviors of our graph. And so this is a polynomial, and so the end behaviors are affected by that leading term, and that leading term in our case was x to the fourth. So we looked at looking at the limit, we called it the limit, as x is approaching negative infinity of that leading term. So if we plug in negative numbers into x to the fourth, well, if you plug in a negative number, raise it to the fourth power, it's positive times this positive coefficient of 1 in front. And so this is going to positive infinity. We also saw that even degrees also had the same end behavior. So as we're going to positive infinity, that also should be shooting upwards to positive infinity, which it does. If you raise a positive number to any power is positive times that positive coefficient in front is positive. So right now we know our end behaviors of our graph are shooting both upwards. So we want to find intercepts. And for polynomials, the easiest is always going to be a y-intercept, and so that's when x is 0. So if we look at f of 0, you're just going to get back your constant. And so when x is 0, we get our y value is 8. Our x-intercept, that's a lot harder. And this is not in the form that we can just factor right away like we were used to. And so let's just use some of the things that we learned. And so let's use the rational zero theorem. So that says we want to look at p divided by q, all factors of our constant, which is 8. So factors of 8 are 1, 2, 4, and 8. And now we want to look at factors of our leading term, leading coefficient, which is 1. So factors of 1 are just plus or minus 1. And so p divided by q, this is always the nicest when our leading coefficient is 1 or negative 1. Basically, p divided by q is just your p-value, factors of your constant. So plus or minus 1, 2, 4, and 8. So this is where Descartes' rule of signs could be helpful to determine how many possible zeros that we have, positive zeros. So that's where we want to look at the number of sign changes. And so if I go back up to f of x, and I look at the number of sign changes, well, I have a positive 1x to the fourth to a negative 1x cubed, that's one sign change. Then I have a negative x cubed to a negative x squared, nope. Negative x squared to a positive 8, that's another one. And positive 4x to positive 8 is not. And so we have 2 sign changes. So I have that number or that number minus an even number. So 2 minus 2 is 0. So there's either 2 or 0 positive real zeros. So let's look at the possible negative real zeros. So I have to look at f of negative x. And so if I plug in negative x wherever we see an x in the original function, so negative x all raised to the fourth power. Well, if I simplify that, that's the same thing as x to the fourth. Negative, and then I have a negative x cubed. And that negative x cubed is in parentheses, but if I multiply that out an odd number of times, that's negative with a negative coefficient out front. So this is really plus an x cubed. Negative 6x squared, or the negative 6, and then that negative x is squared, that's positive. So it stays as negative 6x squared. 4 times negative x is minus 4x, and then plus 8. So sign changes, x to the fourth to x cubed, no, x cubed, excuse me, to minus 6x squared is negative 6x squared to negative 4x is not, and negative 4x plus 8 is. So there's 2 sign changes. So there's either 2 or 0 negative real zeros.
I'm sorry, how do we get the or 0 again?
You always have to look at the number of sign changes it is and then keep subtracting an even number. So keep subtracting 2 until you either get to 0 or 1. So if I had, for instance, if I had 8 sign changes, then I'd have to look at, there's either 8 of those zeros, or 8 minus 2 is 6 of those zeros, or 6 minus 2 is 4, 4 minus 2 is 2, 2 minus 2 is 0. It's not possible to have a negative number of zeros. And so that would tell me there's either 8, 6, 4, 2, or 0. Either negative or positive, depending on which one I was looking at. Okay, so now that we did that, we have things that we can help us find that, again, X-intercepts. These are the numbers that we're going to test. My Descartes rule signs didn't really help me eliminate any right now, but it can help me later. So let's just start with 1. So let's look at 1 and see if it's a 0 of our polynomial. So we're going to put 1 up here, and we're going to use our synthetic division. So synthetic division, we want to list our coefficients of our original polynomial, in this case, so 1, negative 1, negative 6, 4, and 8. Again, you want to make sure that all those terms are listed. There's no missing term with the descending order of powers. In this case, there was not, so we're good. So bring your first number down. Multiply it by the c, so 1 times 1 is 1. Sum that column, negative 1 plus 1 is 0. Multiply that sum by your c, 1 times 0 is 0. Put it underneath the next number. Sum that column, negative 6 plus 0 is negative 6. Multiply that by c, so negative 6 times 1 is negative 6. Sum that column, that's negative 2. 1 times negative 2 is negative 2, and this gives me 6. So x equals 1 is not a 0. So it's not going to cross the x-axis there. If it was a upper bound, because this is a positive number, these would all have to be positive or 0, and they're not. So let's look at the next number in our list. So let's try 2. So we still have the same coefficients because we haven't found a 0 yet. So 1 minus 1, negative 6, 4, and 8. Bring the first number down and multiply it by c. In this case is 2. So 2 times 1 is 2. Sum the column, negative 1 plus 2 is 1. 2 times 1 is 2. So in that column, negative 6 plus 2 is 4. 2 times 4 is 8. Sum that column, 4 plus 8 is 12. 2 times 12 is 24. 8 plus 24 is 32. Okay, so x is not crossing the x-axis at 2, and it's not a zero of the polynomial, but this is an upper bound.
Wouldn't 6 minus 2 be negative 4?
Ah, shoot. Good, maybe it works. I was thinking then we have complex numbers. Okay, let's go back and let me erase some of this. Okay, so negative 6 plus 2 is negative 4. Gotta slow down. 2 times negative 4, that's negative 8. 4 minus 8 is negative 4. 2 times negative 4 is negative 8. Yay, it's 0. So x does equal 2. And it's not necessarily an upper bound because these are not all positives. It's possible that this 2 can work again. I want to break this down though, because it's easier to find the zeros if we keep breaking that polynomial into simpler factors. And so we know x minus 2 is a factor. And this bottom row, well, what do we start with? The 4th power, so this is going to start with a x cubed. So this is x cubed plus x squared minus 4x minus 4. This is equal to our original polynomial f of x. So I can continue with my process. I actually, looking at this degree 3 polynomial, that does exclude that 8 is a possible solution or negative 8, because look at my constants, negative 4. What I'm showing you right now, though, are tricks to help you factor or help you find zeros. Notice this polynomial, this cubic, it's actually factorable by methods that we've done before. There's 4 terms here, and notice we can factor by grouping. So these are just, again, tricks to help us where before we would have needed a graphing calculator and wouldn't have been able to do this. So let's just factor this a little further by just using factoring by grouping. So x cubed plus x squared, we could pull an x squared out of both of those terms. If we did that, we would be left with an x plus 1. That last 2 terms in here, a negative 4 is in common, so let's pull a negative 4 out. And we would have x plus 1. And so we have x minus 2, and then x squared minus 4. X squared minus 4 can be pulled out. I'm sorry, x squared plus 1 can be pulled out, but then you'd be left with x squared minus 4. So again, we can use tools that we know for factoring. You have a difference of squares there. So x minus 2, bring down the x plus 1. The x squared minus 4 can be factored as x minus 2, x plus 2. And so we just factored our polynomial f of x. Oh no. Hold on. Okay, I was worried that I had used the coefficients of f of negative x when I put it down here. I didn't. Okay, we're good. Okay, so this whole thing was just to find our x-intercepts. Our x-intercepts are going to occur when f of x is equal to 0. and we factored everything down so we can see when this is equal to 0. Is when x is positive 2, when x is negative 1, when x is positive 2 again. I don't have to write that, but it does help me that I know this is multiplicity more than 1. It's multiplicity of 2. And then x equals negative 2. And so multiplicity, if it was an even multiplicity, that told me that it was just going to touch the x-axis there. And then the odd multiplicity told us that it was going to cross the x-axis. So notice, just to see, all of these were rational zeros, and they were all in our list of our possible rational zeros. Multiplicity, again, count. So if we counted the number of zeros, multiplicity 2, that's like 2 zeros, even though they're the same. Negative 1 has 1 and negative 2 has 1. It's a degree 4 polynomial, 4 zeros. And so now we can kind of put together what we had done before to graph it. And so we technically only can do a rough sketch, but it's important, the values that we do know. And so we had an y-intercept, was that negative? That was positive 8. And at 2, it's just going to touch it. And we have one at negative 1 and negative 2. And we know it's going to cross it. We also know the end behaviors are both shooting upwards. Not technically vertical. Okay, so it's crossing it here. It has to go below the x-axis. It has to turn around. It has to cross again at negative 1. We know it's going to cross the y-axis at 8. We're not sure if it's going to change right here or if it's going to continue to go up. It could have changed direction before and come back down and hit that. We don't know, but we can graph it on Desmos and get a kind of an idea. So it could, we don't know, but it's going to have to come back down, hit this x-axis at positive 2 and turn back around. And then that's where, if you have some like math lab questions that are dealing with asking you to find that max or min, we again don't know that. You'll learn techniques to do that without a graphing calculator once you get to calculus. But you can use that Desmos and plug it in there and get some estimates and get a better kind of sketch or idea of what it looks like. But we have a general idea of what's going on, and we have some major points in here and what's going on with our end behaviors. So kind of putting everything together that we learned from this chapter. Okay, so we're almost done with this chapter. The last bit is adding on to what we have just been doing, but now talking about complex numbers as being part of our solutions. If we're talking about graphing, and we get a value, a complex number, then that's telling me it's not going to cross the x-axis for that piece of that polynomial. Let me see. Let me give another page. Okay, so this is the last section, 5.7 in chapter 5. And this is called complex zeros. And the fundamental theorem of algebra. Which I've been basically telling you the whole time, but I just haven't labeled it as a fundamental theorem of algebra. Basically, if you have an nth degree polynomial, we can rewrite that polynomial as a factor of n linear factors. I was saying and or quadratic, but those quadratic that had complex zeros as its solutions or imaginary numbers, those can also be written as linear factors. And that's also including multiplicity. So if something occurred twice, x minus 1 quantity squared, it still could be written as linear factors, x minus 1 times x minus 1. Okay, so we got some theorems. Let's just do the fundamental theorem of algebra. So it says for every complex polynomial function f, of degree n, which is greater than or equal to 1, has at least one complex. Zero. And based off of that is another theorem. That's the one I really was telling you about. So every complex polynomial function of degree n greater than or equal to 1 can be factored into n linear factors, not necessarily distinct, of the form ... So let's just say furthermore. The polynomial can be factored into n linear factors. Not necessarily distinct. Two C's and two S's. Distinct. Okay, so one thing to remember when it's saying complex zero, remember complex numbers are actually, real numbers are actually a subset of your complex numbers. So for instance, 2 is a real number, but that is actually in the form we could write it complex number 2 plus 0i. It's just that the imaginary part of our real number is, of real numbers is just 0. So let's other thing that you need to know, and then I think we can jump into some examples. We also have a conjugate pair theorem, which is helpful to know. So suppose f is a polynomial function whose coefficients are real numbers. If r equals a plus bi is a zero of f, then the complex number r equals a minus bi is also a zero of f. So again, so if f is a polynomial, whose coefficients are real numbers, then if r equals a plus bi is a zero of f, then the complex conjugate So to denote conjugate, you can denote that with a bar over it, this horizontal bar over r. So that's saying the conjugate of r. And basically, we already talked about this. It's changing the sign in between the real part and the imaginary part. And let me rewrite this. This was r was equal to a plus bi. So the conjugate, that r with the horizontal line, is a minus bi. Is also a zero of f. Okay, I'm not going to prove that is true. We're just going to assume that the people that proved it before were right. Let me pull some examples. To use the information given about the polynomial function, f whose coefficients are real numbers, and find the remaining zeros of f. Okay, so you're given that it's a degree 3 polynomial. Your zeros are 4 and 3 plus I. Let's do this in multiple pieces. Part A, let's find the remaining zeros. Okay, well, it told me it's degree 3. It told me it had real coefficients, and it's giving me 1 0 is 4. It's giving me another 0, 3 plus I. And so just by that theorem I gave you, by the conjugate pair theorem, then I know that the conjugate of 3 plus I is also a 0, and that would be 3 minus I. So by conjugate pair theorem, three minus I is also a 0. It's a degree 3, so I know I have 3 zeros. 4 is 1, 3 plus I is 1, and 3 minus I is 1. So if it asked for a polynomial that has those zeros, so find a polynomial. with those zeros. Okay, well, if x equals 4 is a 0, then I know x minus 4 has to be a factor. So I can do the same thing with my imaginary numbers. So I know if x equals 3 plus I is a 0, let's get that set equal to 0. So let's subtract 3 on both sides and let's subtract I on both sides. Those are not like terms, so I would just write it as x minus 3 minus I equals 0. So I know then x minus 3 minus I is a factor. So if x equals 3 minus I is a 0, which it has to be by the conjugate pair theorem, set that equal to 0, we know x minus 3 plus I is a factor. So we have the 3 factors. We have x minus 4 is one factor. We have x minus 3 minus I. Oops. Is a factor, and x minus 3 plus I is a factor. Let's say they don't want it that way. Let's say they wanted it expanded. When you expand, multiply the factors, the complex factors, the conjugates together. There's basically a difference of squares, so things are going to cancel out with one another. And so that we shouldn't have any more imaginary numbers once we do this. So x times x, I'm going to distribute x to all terms. So x times x is x squared, x times negative 3, so that's minus 3x, x times I, so that's plus ix. Distribute the next term, which is negative 3, to all terms inside the third parentheses. So negative 3 times x, so that's minus 3x. Negative 3 times negative 3 plus 9. Negative 3 times positive I is negative 3i. And now distribute the negative I to all 3 terms. So negative I times positive x is negative ix. Negative I times negative 3, that's positive 3i. And negative I times positive I, that's negative I squared. But remember, I squared equals negative 1. So negative of negative 1, so this is really plus 1. Let's, before we distribute, combine like terms inside now that second parentheses. So there's only one term with an x squared. Bring it down. Let's look at all the real coefficients that have just a single x. So I have a negative 3x and a negative 3x. So that's a negative 6x. Now let's look at all the terms that have an imaginary coefficient with just an x. So here we have a ix and a negative ix. So those actually cancel one another. Looking at our real numbers, so I have a plus 9 plus 1, so that's a plus 10. But my complex numbers, negative 3i plus 3i, those are going to cancel with one another. So just like I said would happen, this should not have any more complex or imaginary numbers as coefficients. And so now let's distribute and rewrite this. So distributing our x to the x squared minus 6x plus 10, we get x cubed minus 6x squared plus 10x. now distribute -4, so -4x squared plus 24x minus 40. And so combining like terms, there's only one x cubed term, but a -6x squared minus a 4x squared is a -10x squared. A positive 10x plus a 24x is a plus 34x. And then only constant we have is minus 40. Okay, so that's one single out of an infinite number of polynomials that is of degree 3 that has those 3 zeros. The reason why I say infinite is because we can multiply this by any non-zero real coefficient and have the same zeros.
I'm gonna be honest, you kind of lost me when we were going backwards from the imaginary numbers and trying to find the factor from that.
Yeah, that's the imaginary numbers. That tends to get students, especially when there's more than one term in there. And so that's where I was thinking that and how we were doing that. Are you okay when it was a real number finding the factors?
Yeah, you just make it x minus 4, or you put it back on that side of the equation.
Yeah, so think of it the same way when it's a complex number is your solution. So if we set x equal to that and we try to get x by itself, set it equal or get it equal to 0. So we'd have to subtract 3 on both sides. So we'd have the x minus 3. And then we'd have to subtract this I on both sides to move it over. So minus I equals 0. So this would be the factor. It just kind of looks ugly because it's 3 terms.
I was thinking way too hard about that. I didn't realize that you're using the second factor. I didn't know where you got that, and I looked back up in the work and I said, okay, I get it now. Sorry.
Okay, yeah, no problems. There's a lot going on in one problem, and you guys are going to see that. The more you go on in math, you're going to have all these different concepts coming in at you. And so that's where being, it's going to be really helpful to be strong in your algebra skills when you go on and in your classes in math. So let me see if there's, let's see. Okay, so let's look at where they give us some information. They actually give us the polynomial, and they actually give us some information about a 0. And we have to find the remaining zeros. And so let's say we were given that f of x is equal to, x to the 4th power minus 7x cubed plus 14x squared minus 38x minus 60. And they give us that 1 plus 3i is a 0. Find the remaining zeros. So there's multiple ways that we can approach this. So what I would do is, knowing that I have a 0, 1 plus 3i, I would use my synthetic division. I would know that when I use my synthetic division, if 1 plus 3i is a 0, my remainder has to be 0. I know that if 1 plus 3i is a 0, by that complex conjugate, or the conjugate zero theorem, that 1 minus 3i is also a 0. And so I can break it down that way. The other way that you guys can do it is we can think of this, we can find our factors. We can multiply those together. Those would give us real numbers, and we could do long division of polynomials. And it really depends. Let's do this 1 plus 3i up here. Okay, because we're dealing with complex numbers, we really actually need a lot of space when we're spacing out our coefficients of this polynomial. So this would be 1, -7, 14, -38, and 60. Again, if I don't get 0 back here, I know something's wrong with my arithmetic. So let's bring down our first number, 1, multiply it by c. 1 times 1 plus 3i is 1 plus 3i. So this is where being able to add real and complex numbers together is helpful, which we've already talked about. So add the real parts together. -7 plus 1 is -6 plus 3i. I'm going to have to multiply these together. I can't do that in my head. So I'm going to put them down here, and I'm just going to distribute and do it. So I have to do 1 plus 3i times my -6 plus 3i. So distribute, I get -6 plus 3i. Distribute my 1, distribute my 3i. 3i times -6 is -18i. 3i times 3i. Well, that's positive 9i squared, which is -9. Add my real parts, -6 minus 9, -15. Add my imaginary parts, 3i minus 18i is -15i. Okay, so this is going to go below my next number. So -15 plus -15i. So sum that column. 14 minus 15, that's -1 minus 15i. Okay, so again, I got to multiply that by my 1 plus 3i. So if I distribute 1 times -1, so that's -1 minus 15i. Distribute my 3i. -3i times -1 is -3i. And 3i times -15i. Well, 3 times -15, that's -45. -45i squared is positive 45. Add real parts. 45 minus 1 is 44. -15i minus 3i is -18i. Let's put that back underneath. And then let's sum our columns. So -38 plus 44, that is 14 minus 18i. Okay, I hope that's a constant. We're going to multiply 1 plus 3i, and I hope that's -60, times 14 minus 18i. Distribute my 1, I get 1 times 14, that's 14. 1 times -18i is -18i. And something's wrong, I think.
Yeah, it's 6, not 14.
6, 14. Thank you. Yeah, you're right. 6 minus 18, 6 minus 18i. If I pull a 6 out of there, you'll notice that that's actually their conjugates, 1 plus 3i, 1 minus 3i. But anyways, let's just distribute. So this gives me 6. This gives me -18i. 3i times 6, that's plus 18i. That has to cancel, which they do. And positive 3i minus 18i, 3 times 18 is 54. That's -54i squared, so that's a positive 54. 6 plus 54 is 60. Did I write that down wrong? Should that be minus 60? Yay, this I should have copied as minus 60. And this is 0. Okay, the second time we do this, it's not going to be too bad. It looks like it's ugly because these are imaginary coefficients, but we know that 1 minus 3i is also a 0. But it's going to come out really nicely. We're going to use this bottom row. This is degree what? Well, our original was degree, I believe, 4. So this is degree 3. So our bottom row of this one was going to be degree 2. So let's put this up here. So 1, negative 6 plus 3i, negative 1 minus 15i, and 6 minus 18i. Bring our first number down, multiply it. So 1 times 1 minus 3i, that's 1 minus 3i. So sum this, negative 6 plus 1 is negative 5. 3i minus 3i cancels. Distribute the negative 5. So negative 5 times 1 is negative 5. Negative 5 times negative 3i, that's plus 15i. So now when we sum this, the real part, negative 5 minus negative 1, that's negative 6. Negative 59 plus 15i cancels. Distribute our negative 6 times 1 is negative 6. Negative 6 times negative 3i, that's positive 18i, which is what I wanted. This is 0. So this is a degree 2. We're almost there. So this polynomial is x squared minus 5x minus 6. So we're trying to find zeros. Do we know when this is equal to 0? Well, that one's nice because that one's factorable. There's two numbers that multiply to negative 6 and add to negative 5. So this is x minus 6, x plus 1 equals 0. So x minus 6 is 0 when x is 6. X plus 1 is 0 when x equals negative 1. And we said 1 minus 3i was also 0, and we were given that 1 plus 3i was a 0. So given 1, 0, you should be able to find the remaining zeros. We should have been able to do that without even be given that complex number as a 0. We should have been able to break it down using the rules that we just learned from the previous section. We would have found the real pieces. We would have been left with a quadratic. And when we applied the quadratic formula, this is what we would have gotten for our zeros.
So how did we know to do it the second time?
Because we were given this 1 plus 3i was a 0, or was it the 1 plus 3i? We know by that conjugate pair theorem that 1 minus 3i is a 0. So we were given this one is a 0, so we know one more of them, and so I could do it there.
Oh, are they two separate things?
Yeah, those are two separate numbers. So I'm just applying it to my bottom row so that I can keep breaking this down into lower degrees. Does that make sense? Okay, so that is, we pretty much did, we just finished, and that's what my goal was, to get these two sections done today. So we just finished chapter 5. Chapter 6 is, we're going back to review of some algebra stuff. So we're going back to looking at functions, inverse functions, which gets you into exponential and logarithms. Chapter 6, since it's a review, and then I think most of the rest of the course is not review, I am planning on getting through this, all of chapter 6, within hopefully 2 days, but possibly 3 days. So just kind of give you a heads up where we're at.